Assalamualaikum and hi everyone. Now we are going to continue with our chapter 2, homogeneous semiconductor, focusing on density of states and Fermi-Dirac statistics. We have learned that in a semiconductor, current can be carried by electrons in the conduction band and by holes in the valence band or both. In intrinsic semiconductor, carriers in intrinsic semiconductor are not enough to make it a conductor. In order to increase the conductivity of a semiconductor, it is doped with other materials, forming what we call extrinsic semiconductor. There are two types of extrinsic semiconductor. One is the N-type semiconductor, made by doping a semiconductor with material from group 5. The group 5 materials will donate free electrons to the semiconductor, thus it is called donor. In the process, there is no increase of holes in the semiconductor, thus N node is larger than P node. Second one is the P-type semiconductor. P-type semiconductor, which is made by doping a semiconductor with material from group 3. When group 3 material bonds with group 4 semiconductor, there is a missing electron site or empty site, which is considered as holes. When other electron from other semiconductor atom fill up this empty site, the group 3 material will receive electron. Thus, it is called acceptor. In this case, the number of holes in the semiconductor increases, but there is no increase in number of electrons. Thus, P node is larger than N node. Further, in order to understand the semiconductor characteristics, we need to understand the position or distribution of carriers in the semiconductor. Thus, the objective of this subtopic is to understand the density of states and the related Fermi-Dirac statistics of electrons and holes in a semiconductor. We need to understand how the electrons and holes are distributed in the semiconductor. This can be done by understanding the density of states. Density of states is the mathematical representation that shows how the allowed states are distributed in the valence band and in the conduction band. We know that there are energy levels exist in the material. Thus, SE, or density of states, represents the number of allowed states per unit volume per energy. Allowed states is defined as the position where the electrons are allowed to exist along the energy level. In the band gap or forbidden gap, I have said earlier that there is no electron in the forbidden gap because electrons are forbidden to be there. It is because there is no states available in the forbidden gap. We also need to take note that the presence of states does not mean that electrons exist. It can be empty state without any presence of electrons. So how to calculate or predict the population of electrons? There is a probability function known as Fermi-Dirac function, denoted as Fe, that gives the probability of an electron occupying a given state at an energy E in an allowed band. Thus, the electron concentration distribution function is given as Ne equals to Se and Fe. And since hole is the non-existence of electrons, thus the hole concentration is the product of Se and 1 minus Fe. So what does Se tells us? The density of state function for conduction and valence band are given here. It is closely related to the effective mass of electrons and holes. Both density of states can be represented in this figure. From the figure, density of states for the conduction band is 0 at the band edge, meaning that no electrons can stay at the band edge. Further, going deeper, or in this case going higher into the band, more states are available. For the density of states of the valence band, similarly, the density of state is 0 at the band edge, and further deeper into the valence band, the density of states increase. Now that we know how and where the allowed states are situated, we need to know probability of the existence of electrons and holes at the conduction band, valence band, and band gap. Only then we can know how the electrons and holes are distributed. This is the Fermi-Dirac probability function. It is a probability that an electron occupies a given state at an energy E. EF here is called a Fermi level. It is a conceptual reference energy. K is Boltzmann's constant and T is temperature in Kelvin. Under equilibrium conditions, the Fermi function Fe is the probability that an available state at E will be occupied by an electron. For the probability that the state is empty, it is 1 minus Fe. So 1 minus Fe is the probability that an available state at E is empty, which in the case of in the valence band, it will be occupied by a hole. Thus, for holes, the Fermi-Dirac function for holes is given as Fpe equals to 1 minus Fe, which can be further rearranged as these two equations below. We have known that Fermi-Dirac characteristics or Fermi-Dirac probability shows the probability of electrons exist at a given state at a given energy level. This can be plotted into this graph. X-axis is energy level and y-axis is the probability function Fe. We focus at the exponential term, exponential E minus Ef over T. For T equals to 0, at E smaller than Ef, the exponent factor will become negative infinity, thus approaching 0. This results to Fe becoming to 1. When E is larger than Ef, the exponent will become exponent infinity, resulting Fe becoming 0. To loosely imagine what is happening at 0 Kelvin, when the probability Fe is 1, this means that 100% sure that below Ef, electrons exist at the given states. This is due to at T equals to 0 Kelvin, we know that the electrons are all freezed due to having no energy to move. Thus, all the states at the low energy are filled and the valence band is fully occupied. Looking at the energy larger than Ef, the probability is 0, meaning that there will be no electrons at these energy levels. Relating to this figure, since the electrons have no energy to jump to the higher states, no electrons exist at the level above Ef. At higher temperature, the electrons will have enough energy to jump to higher levels as shown in this sketch. Thus, the probability near the Ef will be lower, and at the higher energy larger than Ef, the probability will increase from 0 because there will be electrons at the energy levels above Ef. We now identify the levels below Ef as Ev and above as Ec. Thus, the plot can be drawn as this figure for the temperature dependence. At T equals to 0 Kelvin, the probability is 1 for energy level lower than Ef and 0 if it is above Ef. As T increases, the probability below Ef reduces and those above Ef increases. So what is actually a Fermi level? Fermi level, Ef, is not an existing energy level. It is conceptual and it is created to allow mathematical calculation of the electron and hole distribution. The Fermi level determines the probability of electron occupied at different energy levels. The closer the Fermi level is to the conduction band, the easier it will be for electrons in the valence band to transition into the conduction band. So for these three types of semiconductor, for intrinsic semiconductor, since the number of electrons and holes are the same, the Fermi level must be at the middle of the band gap. Thus, Ef equals to 1 over Eg. The Fermi level for intrinsic or intrinsic Fermi level is denoted as Ei, and Ei must always be equal to 1 over Eg. For n-type material, electrons are more than holes, so Ef must be close to conduction band Ec. For p-type, more holes than electrons, thus Ef is closer to valence band Ev. We draw Ei for every material for reference. In n-type, Ef is larger than Ei, and p-type, Ef is smaller than Ei. EI can have fixed values because the band gap for each material has fixed values. So for the summary, density of states SE is the allowed states that are distributed in the valence band and in the conduction band. Fermi-Dirac probability function is the probability that an electron occupies a given state at an energy E if the state exists. Fe is given as the equation below. The probability for holes is 1 minus Fe. The Fermi level determines the probability of electron occupancy at different energy levels. The closer the Fermi level is to the conduction band energy, the easier it will be for electrons in the valence band to transition into the conduction band. The three-band diagram for the three materials, intrinsic semiconductor, N-type semiconductor, and P-type semiconductor is shown here. The EI, or the intrinsic Fermi level, for the intrinsic semiconductor is overlapping with the Fermi level of the intrinsic semiconductor. So EI is equal to EF. For N-type semiconductor, EF is larger than EI, and for P-type semiconductor, EI is larger than EF.